Hello everyone, my name is Omar and I am a postdoctoral fellow in sedimentary geology here at the University of Ottawa. And this work is a joint collaboration between the University of Ottawa and the Geologic Survey of Canada. And before I begin, I'd just like to thank the committee for organizing this conference, all the work that they put forth in it, and as well as to acknowledge my co-authors on this work. So to set the stage, geologic context, this is a Laurentide ice sheet. At its maximum extent, it's about 2 to 3 kilometers thick in certain parts of Canada, that upon melting produces a substantial volume of meltwater discharge. And this sediment-laden meltwater discharge was dispersed into the isostatically subsided Champlain Sea basin, the maximum extent of which is shown, of the Champlain Sea is shown in this map. And the city of Ottawa is the focus study area for today's talk. So the rationale for studying the Champlain Sea basin is driven both by its great societal interests due to the potential susceptibility of these sediments to retrograde landsliding. As well, these sediments in the Ottawa and St. Lawrence River Valley serve as a regionally extensive aquitard, and so their integrity is also of great interest. This is a map in East Ottawa showing the distribution of these two boreholes. I know we've looked at 2 talks that have shown this, but for those of you who are just joining us now, BC2 and BC16, they're separated by a distance of about 3 kilometers in the municipality of Orleans in East Ottawa. And in fall 2019, scientists at the GSC, in conjunction with other groups, had continuously cored these 2 boreholes. And with these sediment cores, they were sent to Quebec City, where they were scanned using a medical-grade computed tomography scanner, a CT scanner. And the CT scan data set allowed for the reconstruction of the depositional history of the stratigraphic succession. And so beginning at the base of the succession, there's a thin, few meter thick interval of these mud rhythmites, parallel laminated. They look like classic varves. And this unit abruptly transitions into a few meter thick interval of bioturbated mud. Notice, go from nicely stratified rhythmites in the base to this bioturbated unit. And this bioturbated unit in turn abruptly transitions into this texturally diffuse, we call banded mud unit, that in turn abruptly transitions into this unit consisting of well-developed parallel stratification, as you can see in the CT scan image here, that is in turn intercalated with more diffusely stratified mud beds. And in the upper part of the succession, we do encounter these beds of deformed mud that occur intercalated with the well-stratified and diffusely stratified mud beds. But the use of a CT scanner, or CT scan data set, and this provides sedimentological detail at about a 0.5 millimeter scale, being that of the CT scan resolution. It allows for the identification of bedding, of lamina, sedimentary structures, macroscopic burrows, and presence of bioturbation. But what about sedimentological details at a sub 0.1 millimeter scale, that of sediment composition and texture and fabric? So in order to determine these details, we sampled the cores. And so bear in mind, these are uncompacted, basically unconsolidated mud from which we were able to produce polished thin sections. And these polished thin sections were examined using an optical petrographic microscope. And the polished samples were then coated for SEM analysis. And this microtextural data that was collected through the summer and the early fall opened the avenue for a number of research questions that could be addressed. First of which I'll address is, what is the texture, the fabric, and the origin of biogenic structures in Champlain Sea mud? And so a number of different burrow fills were recognized based on the texture and fabric of the sediment. The first of which is a burrow fill consisting of a clay-rich fill, as you can see here, marked by a silt-rich lining, as you can see here. And so these burrows are several hundreds of micrometers in their diameter. They're often elliptical to subcircular in cross-section. This photomicrograph shows an assemblage of these clay-rich filled burrows that are lined by silt. Take it one scale further down to the SEM scale. This shows the fabric of these burrow fills. Note the elliptical morphology. The detail on the right shows the clay-rich fill. It consists mostly of clay-sized sediment. There's some dispersed, very fine to fine silt as well within the fill. And then it's sharply lined with its silt-rich lining, consisting mostly of silt-sized sediment. The other type of burrow fill that was recognized is that of a silt-rich fill that has a distinctive clay-rich lining. These burrows are typically on the order of about 150 to 300 micrometers in their diameter, also elliptical to subcircular in cross-section, and they're easily differentiated from the mud matrix. So here you can see the silt-rich fill, which makes up the core of the burrow, surrounded by its clay-rich lining. And here you can recognize in this photomicrograph, you can identify the presence of several of these burrow fills. Notice the distinctive birefringence of the clay-rich lining and the silt fill, which is quite recognizable and can be distinguished from the mud matrix. We take it one scale further down to the SEM scale. So note the texture and fabric of these silt-rich fills consists mostly of silt-sized sediment, surrounded by a few tens of micrometer thick clay-rich lining. Right, that can be quite variable depending on how the burrow has been intersected in terms of whether it's an oblique cut or. And the third type of burrow fill that was recognized is a clay-rich fill that has a clay-rich lining. Now, difficult to determine the fabric at the optical microscope scale, but the fill is structureless. It's clay-rich. The lining consists mostly of clay-to-fine silt. This photomicrograph shows a dense assemblage of this type of burrow fill. At the SEM scale, here you can see the structureless nature of the clay-rich fill, and so the fills are only a few tens of micrometers in diameter, marked by a clay to very fine silt-sized lining, of which the particles are aligned parallel to the burrow boundary, as you can see here. And the burrow boundary is in turn marked by medium to coarse silt-sized sediment. And so what was recognized were three burrow types in the succession. But also important to note is that along bedding parallel sections is the architecture of these burrows, which consists of these sinuous forms, as you can see here. So these are CT scan images. And so the different types of burrow fills, their size, which is a few tens to several hundreds of micrometers in their scale, as well as their architecture. Well, these resemble those produced by modern marine meiofauna. Meiofauna simply referring to small organisms between the range of 0.045 micrometers to 1,000 micrometers. The structure of the clay-rich burrow fills, well, this type resembles those generated by deposit feeding in faunal organisms, whereas the distinctive, well-developed clay-rich lining, well, this fill and the passive fill, that of the silt-rich fill, well, this resembles those of organisms that generate dwelling and or feeding structures. The second research question I want to address was, what is the occurrence and origin of iron sulfide minerals? And what is the association of these minerals with biogenic structures? And so iron sulfide takes the form of pyrite, mostly of pyrite in the succession. And the pyrite occurs in a crystalline form in a number of different occurrences. The first of which, and this is the most commonly occurring form of pyrite, is that in the form of these elongated clusters of rhomboids. So both of these SEM micrographs, electron micrographs, show these elongated voids that have been infilled with rhomboidal pyrite. And so the pyrite rhomboids are typically on the order of about 5 to 15 micrometers. The other form of pyrite that was recognized are these irregularly shaped concretionary masses, as you can see here. And so the pyrite is kind of poorly developed has a poor crystalline habit, kind of clustered together, and these are typically on the order of about 60 to 100 micrometers. And lastly, pyrite also occurs as euhedral crystals that fill the interstitial pore space in biotite crystals. So these, both of these electron micrographs show pyrite in a euhedral form that has precipitated along the within the interstitial pore space between these expanded mica flakes. And so the extensiveness of the pyrite cement can range from locally developed, as shown in the example on the left, to extensive, as shown in the example on the right, almost completely infilling the space between the cleavage planes. And so the first form of pyrite, that of these framboid-filled structures, well, these structures morphologically resemble those produced by a burrowing Meiofaunal. Pyrite framboids, these form in sediments when pore water sulfide from organic matter decomposition reacts with dissolved ferrous iron. And the source of the organic matter is thought to have been directly from meiofaunal activity, that of mucus trails and mucus secretions left behind by the burrowing infaunal organisms. In other words, animals burrow through the sediment, they secrete mucus, organic slime to ease their passage, and then decomposition of the mucus trails left behind by the infaunal organisms can provide a food source for sulfate reducing bacteria, which leads to localized pyrite precipitation. The other form of pyrite that occurs is poorly crystalline, kind of irregularly shaped concretionary form. Well, this is interpreted to have precipitated in pore spaces that were not significantly enriched in reactive organic matter, which resulted in the precipitation of these indiscrete, kind of poorly defined crystals. Lastly, the euhedral pyrite, which occurs between the mica flakes. This is interpreted as localized sequestration of iron into pyrite, where the iron is sourced directly from the alteration of the micrograins, a truly in situ authogenic in-place process. What I also identified through this microtextural study was the presence of authogenic marcasite. Marcasite is a dimorph of pyrite, so it has the same chemical composition but a different crystal structure. And the marcasite occurs as both the replacement and overgrowth of framboidal pyrite within elongated cavities within the sediment. So note the scale. These are on the order of a few hundreds of micrometers, very similar to the clustered forms of framboidal pyrite that fills cavities that we saw a few slides prior. The example on the right, this indicates the presence of pyrite framboids, which you could see at the core of this overall concretionary growth. And the pyrite framboids have then been overgrown by marcasite. And marcasite is characterized by this blocky, kind of tabular morphology. Here are two other examples. Well, one is a magnified view on the right. But what this shows, take your attention to the left, is a pyrite framboid that has been replaced, as you can see here, and overgrown by marcasite, the detail of which is shown on the right. So here's the original pyrite framboid. Then you can see there's been some partial replacement and overgrowth of the marcasite, which is this kind of tabular, blocky, crystalline iron sulfide mineral. So the origin of marcasite in the sediments. Well, marcasite necessitates acidic conditions. Okay, it requires low pH conditions to form. And it's thought that there was an influx, well, the interpretation is an influx of oxygen-bearing fluids that reduced pore water pH. This may have potentially been facilitated by the abundance of tunnels, this network of burrows that was being produced by infaunal, meiofaunal organisms. This combined with most probably a consistent influx of oxygen-rich glaciogenic meltwater that was being discharged and dispersed into the basin during the annual melting season. And both of these serve to most probably enhance pore water advection and the diffusion of dissolved oxygen and directed the downward migration of oxidation fronts. And so the principal mechanism by which we may have a reduced pore water pH is the oxidation of previously formed sedimentary pyrite. And so this mechanism provides the means of producing both dissolved iron and producing the low pH conditions that are necessary and needed for marcasite formation. And the third research question I'd like to address is, what were the paleoenvironmental controls on burrowing in faunal organisms in the succession? So take your attention back to the simplified cross-section between both of the boreholes, showing the 5 lithostratigraphic mud-rich units. The basal part of the succession, that of Unit 1, these mud rhythmites, classic varves, well, these were interpreted to have been deposited in a glaciolacustrine freshwater setting, whereas the overlying strata, that of the biartibated mud and the banded mud, well, these were deposited in a saltwater basin, that of a glacial marine setting. And the first appearance of burrows occurs within the biartibated mud. And spectacular in the succession, you can actually put your finger, the abrupt transition between, glaciolacustrine strata and overlying glacial marine strata. But 2 of the burrow types occur mostly in the lowermost part of the succession, as indicated on the slide here. And the third burrow type, that of the clay-rich fill with the clay-rich lining, occurs exclusively in deformed mud beds near the top of the succession. And so I'll begin with the burrow type shown at the top of the succession that occurs within the deformed mud. And so its exclusive occurrence in that of deformed mud is most probably a consequence of this mud being sourced by a slope failure on the margin of a deltaic margin. Now, this type of burrow fill is not found anywhere else in the succession. It's exclusive only to the deformed mud, and the intercalated strata, that of the well-stratified mud and diffusely stratified mud, in other words, the kind of beigeish, slightly yellowish strata that occurs throughout, do not contain any of these burrow fills. Now, one of the major controls on the presence of biogenic features may have been that of the nature or the chemistry of the basin fluid, that of a change from a freshwater to a saltwater basin fluid. So the incursion of the Champlain Sea provided what is a hospitable environment for these benthic meiofaunal organisms. I should note that pyrite is found exclusively in the samples of which burrows were identified. And so if I take your attention to where we see the lowermost 2 burrow types and their exclusive occurrence in the lowermost part of the succession, and why the presence of burrows are not found above this interval. Well, if I take you to the next slide, this series of plots shows bed thicknesses in the succession. And so from the base to the top of the succession, bed thicknesses increase markedly. But this is the interesting point, is that within each unit, bed thicknesses are consistent. Bed thicknesses are mostly consistent around an average mean bed thickness. They're roughly about 2 centimeters thick in the basal unit. They double to triple in their thickness in Unit 2. They likewise double to triple in thickness in Unit 3. And again, they often double in thickness in Unit 4 time. It seems that the increase in sedimentation rate, in particular that of which is observed in Unit 3, likely serve the principal control on either the ability of these benthic burrowers to thrive at and beneath the seafloor, and the loss of any biologic activity. And just to conclude,
we just have about, oh, sorry, go ahead. I was just going to say we have 1 minute left.
Minute left? Okay, perfect. So future work, the plans for the remainder of this year are to work on this study, which is a comparison of the microtextural characteristics of hyperpycnal flow and hypopycnal plumes, both of which are types of density currents, one of which is a bottom-hugging density current, one of which is a positively buoyant plume. And the purpose of the study is to provide a direct comparison of the deposits of these two types of flow types from the thin section to the optical microscope to the SEM scales, and to potentially address the question, does the texture and structure of these different deposit types influence the geotechnical and reservoir properties of the sediment? And I thank you all very much for your time. Thank you.